Hey everyone. So in this video I like to talk about applications of linear functions. So linear equations and functions, right, things in the form y is equal to mx plus b, or f of x is equal to mx plus b. Right, these things are often used to model and draw conclusions about the world around us, and so I want to take a moment to see if we can examine some different situations and fit in linear equations into the picture. See if we could come up with an equation to really describe a situation. And what this is going to boil down to is really being able to make sense of what slope means and what a y-intercept means in our different situations. But before we can really get there, I want to say a few things first. I want to say that usually in our real situations where we're trying to build an equation to fit the picture, our inputs and outputs have a little bit more meaning than just, an x variable and a y variable. And so usually in these kinds of equations, we want to use some more descriptive variables, right? So instead of something like y is equal to negative 2x plus 8, I might say v is equal to negative 2t plus 8. Kind of the same idea, same structure. Right, so I can kind of think of this t as my input variable and this v as my output variable, and I see a slope of negative 2 and a y-intercept of 0, 8. But maybe in this equation, I might be obtaining the volume of the liquid in some tank at some time t given in minutes, right? Or I might be dealing with an equation here right beside the one I just described. E is equal to 50d plus 100, where maybe d is telling me some sort of distance in miles into some trail, and what I'm getting out is an elevation in feet, right? So, our equations, when we're talking about these real-world applied problems, we might be using variables that have a little bit more meaning. But again, there's going to be a lot of the same structure. And one thing I want to point out in all of these examples is that, we still sort of see this input variable and this output variable for our linear equations. And so usually we call this output variable the dependent variable. Right, so when we're going to be building our equations, we sort of want to kind of keep the same structure as y is equal to mx plus b, and our output variable is going to be called the dependent variable, whereas our input variable is going to be called our independent variable. Right, and this is the case because, when we think about our y is equal to mx plus b equations, usually our outputs, the things we get out for our y values, they depend on what we plug in for x. And so we usually think of y as depending on x, so we call y our dependent variable, or in these sorts of equations where we have a variable that takes on the role of y, we call those the dependent variable. So dependent variable, it's the output, kind of like y, and independent variable, it's kind of like our x variable. And so in this volume equation I have on the left, it kind of feels a little bit more accurate to say our volume in our tank depends on the amount of time that has passed, right? It feels a little backwards to say that the time that has passed depends on the volume in the tank. I mean, you could compute this way, but it just doesn't quite feel like a natural thing. We're really, in this case, measuring the volume, not so much the time and so that's kind of one way you can sort of think about your dependent and independent variables. Which variable or which quantity are you measuring? That's usually your dependent variable. Which quantity depends on the other? That's usually your dependent variable, your y-like variable. Okay, so that's going to be important for trying to build these equations, sort of thinking about which variable takes on the role of x and which variable takes on the role of y. But I want to go back to making a little bit more sense of this sort of y-intercept and this slope. Okay, so let's dig a little bit more into this idea of a y-intercept in one of these kinds of equations. So here I've got the equation v is equal to negative 2t plus 8. And here, maybe I'll just say that the meaning behind this equation is it's giving me the volume of some fluid or some liquid in a tank that's leaking out as time passes. And so here the input variable is t, and it's telling me the time in minutes that have passed. And the output variable is v, it's telling me the volume in the tank, the volume of liquid in liters. Okay, so I want to explore this idea of a y-intercept, and you know, if I had this equation in slope-intercept form, so if I wrote it as, or in y is equal to mx plus b, you know, I might see it as y is equal to negative 2x plus 8. And if I were to ask you what's the y-intercept of this equation, you would tell me it's 0, 8. Y-intercept. It's this point 0, 8. When x is 0, the solution for when x is 0, y is equal to 8. Right? And why do we call it the y-intercept? It's because when we graph out this equation, we see this point 0, 8. It's the point where our line crosses the y-axis. Right, so our line looks something like this. It's got a slope of negative 2, so it goes down as it goes to the right. This is what the graph would generally look like, just a rough sketch. Right, but the thing is that, you know, in this equation, the input variable corresponding to the horizontal axis, it's x, and the output variable is y, and so it makes sense to call this the y-intercept. For these equations where we might be using a different variable, it feels a little funny to call it the y-intercept, so I'm going to call it not the y-intercept, but the vertical intercept. So the vertical intercept. So the y-intercept, I'm going to call it the vertical intercept in these kinds of problems. It's the same thing, it's just that the vertical axis in these situations might not be corresponding to a y variable. We might give it a different variable name, and so I'm just going to say more generically, the vertical intercept of our line corresponds to where the line crosses the vertical axis, the axis going up and down. And so the vertical axis, the line corresponding to v is equal to negative 2t plus 8. It crosses the vertical axis. At the point 0, 8. Right, and here in this case, this is telling us that when t is equal to 0, v is equal to 8. When t is equal to 0, v is equal to 8. What does that mean in words? Well, when t is 0, when 0 minutes have passed, since this leak occurred, there are 8 gallons of liquid in the tank. Not 8 gallons, we're using liters here. 8 liters of liquid in the tank. Right, so here, the fact that 0 time has passed, and we have 8 liters here, this vertical intercept is kind of giving us some notion of sort of a starting amount. Sort of like a starting amount is what this vertical intercept is kind of telling us. When no time has passed, we know that there are 8 liters in the tank. We sort of started with 8 liters in the tank before this leak, before we started measuring this leak occurring. Oops, I have something from a previous attempt at this video. Let's take another equation. Let's take the equation E is equal to 50d plus 100. And let's make sense of the vertical intercept in this situation. So again, you know, I gave some meaning to these variables. D, this tells us that you know, we're sort of examining the elevation along some hiking trail. And that input variable is sort of telling us how far we are into this hiking trail, the distance in miles into this hiking trail. And the thing we're getting out, what we're measuring, is the elevation at that point in the hiking trail. The elevation, and in this case we're going to be talking about elevation in feet. Okay, well, the vertical intercept in this case is, I see that it corresponds to an input of 0. When d is equal to 0, well, this equation is true only when e is equal to 100, right? D being 0 means 50 times 0 plus 100 is what e must be. So we get the vertical intercept. It's the point 0, 100. When d is equal to 0, e is equal to 100. And in words, this means that 0 miles into the trail, the elevation is 100 feet. And again, this vertical intercept is sort of giving us a notion of sort of a starting amount, an initial amount, right? So before we really started going into this trail, we're already at 100 feet of elevation, sort of a starting amount of elevation. That's what this vertical intercept corresponded to. Let me give you one more example. Let's say I've got c is equal to 3p plus 10. Maybe this equation is telling me the cost in dollars to send a package of a given weight. So in this case, the package, the weight is coming from this variable p. The weight of the package is represented by p. Weight in pounds, how many pounds the package is. And the output, the dependent variable, is measuring the cost to ship this package in dollars. Right, and again, if I were to plug in 0 for my input, 0 for p, the weight of my package in pounds, that would tell me that the vertical intercept is this 0, 10. Right, so the solution with an input value of 0, when p is equal to 0, c is equal to 10. And this is telling me, what is this telling me? This is saying that when the package is empty, when it weighs nothing, when it weighs 0 pounds, maybe I shouldn't use the word nothing, when it weighs 0 pounds, the cost to ship this package is $10. Right, the cost to ship this package is $10. In this sense, it's like a starting fee, right? It takes $10 to ship essentially nothing, and any additional weight is going to add up some more cost. But this $10 is a fixed amount that you're going to have to pay no matter what, sort of an initial amount again. That's what this vertical intercept is telling us. So in general, when you're looking at a word problem or a situation and you know you're trying to describe it with a linear equation, a linear function, and you see an initial amount, a starting amount, this corresponds to the vertical intercept. So that's something to be on the lookout for when you're trying to create or cook up these equations. So one more piece of information we need to make sense of is the slope. And so in our slope-intercept form equations, with form y is equal to mx plus b, usually the slope is counted as the change in y divided by the change in x. But in these problems, we might not be dealing with x and y variables. It might be more accurate or general to say that the slope is really the change in the output, or the dependent variable, divided by the change in the input, or the independent variable. And so I want to make sense of how slope looks like in these word problems. And I think one way we can get a sense of things is through the example below. So here I say 3 miles into the trail, the elevation is 4,500 feet. And then 8 miles into the same trail, the elevation is 5,500 feet. So slope, we found it by taking 2 points and computing the slope between them. I want to take this above information and treat them as points and compute the slope between these 2 points. And I think by doing so, we might be able to see how slope will typically look in a word problem. So in this first line, it says that 3 miles into the trail, the elevation is 4,500 feet. Here I can think of this as sort of putting 3 and 4,500 together in some way as an ordered pair, and really there's 2 ways we can imagine doing this, right? 3, 4,500, or 4,500, 3. And now which way feels like the way that I want to take advantage of, or feels the most accurate for the situation? This comes back to identifying sort of an output variable or a dependent variable and an input variable. So which quantity depends on the other? I would say that the elevation depends on how far we are into this trail. And so I'm going to think of my elevation sort of as my dependent quantity, like my output quantities, and I'm going to think of it like my y values here. And so it's 4,500, no, not blue, green here. It's kind of like my dependent quantity, and my 3 miles is kind of like my independent quantity. And I'm really going to be considering writing my point in this form, not so much this one. And so that would tell me that my second line, well, that corresponds to the point 8, 5,500. Right, so again, this is telling me that at 8 miles into the trail, my elevation is 5,500 feet. And so if I compute the slope between these 2 points, well, what does that look like? Well, it's my change in my output, so I'm going to think of maybe this is, first point, this is a second point. I would take 5,500 minus 4,500, and I would divide it by the change in my input variable, or my independent variable. So this is 8 take away 3. And right, I got to make sure I've got the same order, right? So 5,500 and 8, 4,503. And so this difference here is, well, it's 1,000 in the numerator, 500 in the denominator, not 500, 5 in the denominator. And actually, I think to make this clearest, it might make most sense if I also include units. So in the numerator here, this was the elevation, right? So this was the feet. And in the denominator, we were talking about the distance into the trail, the number of miles into the trail. This is 1,000 feet. There's an increase of 1,000 feet across the 5 miles into the trail. If I continue trying to reduce this, well, 1,000 divided by 5 that's 200. And again, we've still got those same units that we're talking about 200 feet per 1 mile. Right, so this slope here is telling me how much I'm changing in my outputs for every single one change in my input. I'm changing by 200 feet in elevation, 200 positive feet in elevation for every single mile, 1 mile I travel into my trail. Right, that's what this slope means. And in general, My pen's acting up a little bit. So in general, the slope in these real-world situations, it's a measurement of a rate of change. It's the rate of change. And maybe just say a little bit more, it's telling us how much output there is per one input, per input. It's telling us how much change in our output values there is per input value. All right, so if I look at the equation that we examined earlier, v is equal to negative 2t plus 8, our slope is this negative 2. Right, this is telling us, remember our input was the time in minutes, v, our output told us the volume in liters. This is telling us that the slope of negative 2, it's really telling us this negative 2 liters per minute is the rate of change of liquid in the tank. We're losing 2 liters for each minute. Every time I increase that value of t by 1, our volume goes down by 2. Or if I look at the equation, E is equal to 50d plus 100, this slope of 50, it's telling us that our rate of change in this situation is 50. Change of our output is elevation, is feet per single mile. Every mile we go into this trail, we expect a 50-foot gain in elevation. And then similarly, in our equation, c is equal to 3 times p plus 10. Right, this slope of 3, this is telling us that there's a $3 increase for every single pound. Every extra pound we're shipping, every single additional pound, there's an increase of $3 in the cost. And so slope is typically this rate of change of the output per individual input. And so when we examine our word problems and we encounter a rate of change, we can recognize that as the slope of our linear equation, our linear function. Oh, whoops, that's a slide I meant to use, but I didn't. Okay, so here we've got a situation, I want to take this in reverse now. We've got a situation and I want to make a linear function, a linear equation that'll model the situation. And so here, there's a lot to take in, but let's go through this together. It says that a weather balloon is typically filled with hydrogen and released to various locations to measure and transmit data about the conditions. So this data might be for the air pressure or for the temperature. But such a weather balloon, it's filled up with hydrogen at a rate of 0.5 feet cubed per second. Right, so what you can kind of imagine is that there's this balloon, and it's filling up with space. Right, we're sort of filling up air into this balloon. Not air, hydrogen. And how much we're filling it up, how fast we're filling up this balloon is with 0.5 feet cubed of hydrogen. So this is sort of, I can kind of think of this block as an amount of hydrogen that's going into this balloon and filling up the inside. And we're filling it up with, the amount we're filling it up with these 0.5 cubic feet per second. Every second I'm filling up with half of one of these hydrogen feet cubes. And so initially the balloon contains 2 feet cubed of hydrogen. So there's some hydrogen already in the balloon, and we have 2 feet cubed. So sort of an amount of space of hydrogen that's filled up inside the balloon. So we want to find a linear function that models the volume of the hydrogen in the balloon at any time t. So our output variable is v, and our input variable here is this time t, right? So our dependent variable, the volume, right? The volume depends on how much time has passed. V is kind of like our output variable, and t is like our input variable. And so here, this volume, we always want to talk about, we want to define our variables very explicitly, right? This is the volume of hydrogen in the balloon, and it's we want to make sure we specify the units. It's in feet cubed. And the time, this is measured in seconds in this case, right? We see in our problem, it says 0.5 feet cubed per second is the rate we're filling up this balloon, and so we're going to measure our units of time is going to be in seconds. Okay, so when it comes to this linear function, we need to identify a rate and an initial amount, and that'll tell us sort of what our linear equation should look like. And here I'm going to use function notation. Right, so we're going to expect something of the form v of t is equal to m times t plus b. Right, and we're saying that m, this is the slope or the rate of change, and b, right, this is the vertical intercept, and it's this initial amount. How much volume, how much hydrogen is there in the balloon when 0 time has passed? Well, we see that actually right here, right? The balloon contains 2 feet cubed of hydrogen initially, from the get-go. And so this vertical intercept, it ought to be the point 0, 2. Right? When 0 time has passed, 0 seconds have passed, we know that there's already 2 feet cubed of hydrogen in the balloon. So, that's one thing. And then we already see another piece of information, that we see this rate, this 0.5 feet cubed per second. Usually when you see that division sign, it's kind of read as per. We've got this 0.5 feet cubed per second. And usually when you see that word per, that's telling you a rate. So here, that's a rate in purple. So 0.5 feet cubed, the change in volume per 1 second. And so v of t, this is equal to 0.5 t plus 2. And so next thing I want to do is I want to sort of use our linear function to come up with, to make sense of this piece of information. We know that the balloon has a capacity of 15 feet cubed. In other words, the most amount of hydrogen that we can fill into this balloon is 15 feet cubed. And so I want to know how long it takes to fill this balloon. And so how can I take this 15 feet cubed and use my function to find out how long it takes? Well, 15 feet cubed, this is a volume. This is a volume. This is an output. I want to find out how long it takes. This is a time. This is an input. If I plug in 15 into my output and solve the equation for t at the time, then I'll figure out how long it took, or how long it would take to get to 15 feet cubed of hydrogen inside the balloon, and I would know exactly the value I'm interested in finding. So I subtract 2 away from both sides. I've got 13 is equal to 0.5 t. To get rid of this multiplication by 0.5, I can divide by 0.5, and maybe a little bit more explicitly, this is 1/2 times t, right? 0.5 is 1/2 times t. And so dividing by 0.5 or dividing by 1/2, that's the same as multiplying by 2. Multiplying both sides by 2, the 1/2 and the multiplication by 2 would cancel out, right? 1/2 times 2 is 1, and so we'd just be left with t on the right side is equal to 26. And so this is saying after 26 seconds of filling this balloon, the balloon is at capacity. It has 15 feet cubed of hydrogen inside it.